Okay, this was regarding the company TESTO. Now I would like to start with some basics regarding the combustion process before we start talking about our analyzers. Actually, this is very general how a combustion process looks like in several segments. We have fuel to be burned, and we have also combustion air, ambient air. And then we have the combustion taking place for different processes like heat generation or power generation, hot steam generation, thermal gas treatment, waste incineration, surface treatment, burning like cement, ceramics, or glass, melting like steel companies, or sintering. These are all processes which need a combustion for producing the product at the end. After this process, we have mostly flue gas cleaning, some devices to reduce SOx or NOx like SCR technologies. Then we have emission control, and at the end, we have the clean flue gas. This is basically how the process looks like, and our instruments can be used at the very beginning in the combustion process to see if everything is taking place correctly. You can use our instrument just to double check flue gas cleaning systems. And you can use our instruments either for monitoring the emissions, for compliance testing, or you can use our instruments as a backup system if you have stationary systems, and in case they fail, can our instruments be used to monitor the emissions for this specific time. When we are talking about combustion, we can divide between ideal, a complete combustion, or a real combustion. An ideal combustion means you have as much oxygen than fuel components. It's just the same amount. And at the end, if you have 3 parts of fuel, you need 3 parts of oxygen, and the result is 3 CO2 parts. And if this is taking place, we are talking about stoichiometric combustion, or if lambda is equal 1. That means the actual needed air in comparison with the necessary air to burn all the fuel completely. But usually that doesn't work in the real world. A real combustion looks like this, that you have always more oxygen present than the fuel components. That means at the end, you have the oxygen molecules which burn the fuel molecules, and then at the end you have CO2 molecules, and because you're providing more oxygen to the combustion, you have also some oxygen left in the flue gas, and this is when we are talking about excess air, or when lambda is greater than 1. And this, because this is taking place in the real world, you have really to be careful that the amount of air you provide for the combustion is just enough to burn the fuel completely, because if you provide too much air, you have a higher flue gas loss, and therefore you lose a lot of energy, which is not really necessary. Oops. Okay, sorry. Here, this combustion chart, this shows you the relation between carbon monoxide, CO, oxygen, carbon dioxide, and the flue gas loss. And in the left part, where lambda is equal 1, we are talking about deficient air. That means there is not enough oxygen present for the combustion. And on the right-hand part, we are talking about excess air. And in every combustion process, if you don't have enough oxygen present for the combustion, you will have very high CO readings. And as soon you start putting oxygen to the combustion process, it starts burning the CO, and at one point there is just enough oxygen present to burn every CO, and then at this point you will have almost the highest CO2 reading because the CO reacts with the oxygen and CO2 will be the result. And at this point where lambda is 1, that means on the right-hand side you provide more oxygen than necessary, and therefore the oxygen value goes up, CO goes down because you cannot burn CO anymore, and also in the same time CO2 goes down because of the dilution of the oxygen you provide in the flue gas, because there is no more oxygen present which reacts with the O2, and therefore in relative the CO2 reading goes down. And to get a feeling with regard to lambda or excess air, it's required to measure CO2, oxygen, and CO. And according to those parameters, you can adjust your burner, boiler, engine, whatever, to your lambda value. And basically, this chart, every fuel, if it's solid fuel or liquid fuel, has its own chart with the CO2 max value, and then according to this fuel, you can adjust your burner for the highest efficiency. Then just one word regarding concentration. The quantity of gas is specified either in grams or milligrams. That means you say, okay, it's 200 milligrams per cubic meter, which is mass related, or you have the reading in ppm without any reference. And mostly the ppm reading is being used to adjust or to tune a burner or an engine, and mostly this, the mass concentration, is being used to show compliance. That means if you have to show your emission values to the authorities. And if we convert our ppm readings into milligrams per cubic meter, there is a few formulas to be used. That means if you would like, for an example, the CO2 reading in ppm, and you would like to convert it to milligrams per cubic meter, you're using 21% oxygen, which is the reference value, minus the O2 base. And this is really depending on the application, because every application has its O2 base. That means just to make sure you can compare readings of different applications, because some applications have excess air, some have reduced air, and you cannot compare really the emission values. Therefore, the government has, requires the O2 basis for different applications. And at the end, you multiply with the specific density of the air at norm conditions at 0 degrees C. This is very important that you refer your readings to norm conditions. And this will take place in the analyzer, because you can show ppm readings or readings in milligram per cubic meter. And the instrument will do this calculation automatically, and you can provide both values. Or in some cases, without any reference, if you would like to show the readings without reference values, like the O2 dilution, it's just the calculation from ppm times the density of the specific air. And here you can see each air has a specific density at norm conditions, like CO is 1.25, SO2 is 2.86, and NO2 is very specific, because here we add both values, NO and NO2, but here for the density is only the NO2 value being used, because at the end of the stack, most of the NO reacts with the present oxygen of excess air, and at the end of the stack you have 90–95% NO2 left. This is why the density of NO2 is being used for this calculation. Reasons for flue gas analysis. There is different reasons you can use flue gas analyzer. One reason is efficiency control and adjustment of burners, boilers, stationary gas engines, gas turbines. We have process control, or we have emission control to show the reading if you comply with the local regulations. If we are talking about efficiency control and adjustment measurements, please have in mind the chart I showed before, which shows the oxygen value, CO2, the CO value, and also the flue gas loss. This is being used for each application or for each specific fuel. And, you know, with regard to the CO2 max value, because our instruments, each flue gas analyzer has a specific list of different fuels with specific parameters behind, like the CO2 value, and therefore you don't have to worry about the CO2 values if you're using different fuels to correct the right lambda or the flue gas loss. And if you have your own fuel, which is not a standard fuel, with our software Easy Emission, you can just enter the fuel-specific data, and the software will calculate all necessary parameters or factors, which can be transferred to the instrument, and based on this new fuel, you can do all your calculations very easily. The examples of important parameters for control and adjustment is oxygen, CO, CO2. The instrument, based on this, will calculate efficiency, excess air, and other important parameters. And this is being used, for example, adjustment and service after plant maintenance or error diagnostics. And the benefits, if you do the service and commissioning, optimization of the combustion process. For example, if excess air is enough to burn all CO completely, or if you don't have too much excess air, which means you will lose a lot of money because unnecessary heat is being pushed through the stack to the ambient. You can increase the efficiency of the burner, and of course, as a result, you can save fuel and money. So this is one of the main applications. And then, you know, it doesn't matter if it's a gas engine, if it's a burner in a coal-fired power plant where you have many burners, if it's just one burner in an oven for producing glass or steel. At every burner, there is potential to just adjust the burner to the right excess air to have the highest efficiency and not to waste money. Then we have process control measurement. This is really depending on the application, but mostly O2, CO, CO2, or SO2 is being measured. There's different examples where you can use our analyzers. You can control a defined gas atmosphere at processes like burning, sintering, surface treatment. That means at different spots within the oven, you can see if there is a O2 leakage or if you have an increase of NOx because of high temperatures, which shouldn't be there. And this is very easy with our instruments because we have different range of sensors, or we have additionally a dilution system. If you have higher concentration in your application, the instrument will switch on the dilution automatically, which means a dilution is like a measurement range extension. But I will show you this later on. Or you can adjust the process burners according to measurement results, because if you burn different fuels, like in a cement plant, you know, heavy oil or tires or waste, everything can be burned, and every fuel has its own specific character, and based on this you can adjust the burner to its highest efficiency. Of course, the result is quality improvement of the production process and the result of the products. And you have also quality documentation for ISO if you're if the plant is certified and you need to show a specific compliance regarding your quality standard. So there's different applications where analyzers can be used in the field. And then we have one part, emission control measurements. Examples for parameters are NOx, NO and NO2, CO, SO2, and CO2. Yes, with our analyzers, you can measure NO and NO2 separately. In some application, it makes sense to get an accurate reading. I will tell you later, specifically at gas engines. And examples of applications is the control of flue gas cleaning installations. That means you can double-check filters, you can double-check SO2 scrubbers, wet scrubbers. You can use our instruments for SCR tuning. This is also very common. Or you can use our analyzers as a backup for stationary analyzers in case they fail, or if you would like to double-check the analyzers if they read correctly. And benefits, of course, keep the emission within limits according to the local requirements and fulfill the requirements of emission regulations. And this has changed a lot in the past because in many countries they wouldn't allow you using a portable analyzer for monitoring emission values for compliance testing because all or most of the regulations were technology based. And yeah, 4 and 5 years ago in the US, they started as first country to change this, and they said, okay, we would like to get rid of technology-based instruments. If they can show that their performance is as good as a reference analyzer, we will allow the user to use a portable analyzer using alternative sensors for showing compliance. And that means with the CTM, the test methods in the US, if you measure according this test method, you can use any analyzer as long you can show the quality of the readings, like stability tests, like calibration tests. Everything can be fulfilled with the analyzer. You can perform those measurements with electrochemical sensors, for example. And they, just to make sure that the reading is okay and that there is no drift during the measurement, they require a pre- and post-calibration before each measurement. So that means every sensor like CO, NO, SO2 has to be calibrated before the measurement, and then they perform the measurement. And then at the end of the measurement, which can be within 24 hours, they have to recalibrate the analyzer just to show that there is no drift or nothing happened to the sensors. And then they are fine and can use the readings as an official measurement.